Oi, sentence VAE, enable next sentence prediction for large language models with faster speed, higher accuracy, and longer context. Big paper today. I'm excited about this one. If it works as well as I think it might, it for one really does not fix literally, but largely get around the quadratic attention problem, the whole memory problem, at least for a while for us. And more importantly to me, it seems like it allows these models to think, quote unquote, in a level of abstraction that I, anyways, predict will be very advantageous for actual learning. Of course, there are still issues to be ironed out, but stick around if you're excited about new architectures, because this is a very, very cool one that, as far as any I've seen in the past few months, I think is one of the most likely to actually be incorporated into mainstream models pretty soon here. We need more results, of course, but I'm excited about it. Let's get into it. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. Disclaimer. So, the huge problem with LLMs right now, right? One token per inference step. This hugely limits the actual computational overhead we have to deal with. Whenever you hear about attention being quadratic in complexity or about transformers taking up so much memory, this is the issue right here, is every single token, which if you're not very aware of what a token is, just think of it as a word. Think of it as a word, right? Every single token takes up a certain its own step in the sequence, and then we have to compare every single token against every single other token. Meaning, if you have 10 words in your sequence, that's 100 comparisons, 10 by 10, right? Or is that right? Squared? Whatever. It's hugely terrible for RAM. Now, in this paper, what they do is create a whole setup that uses a sentence encoder, which is designed to condense the information of an entire sentence into one single token. And by token, they mean an embedding vector, obviously, right? Not an actual token, because the token is the actual text itself. What they mean is we have a sentence with, say, 15 tokens. The sentence encoder takes the 15 embedding vectors of those tokens and compresses them down into one single output embedding or vector, which represents the entire sentence, while the sentence decoder reconstructs this compressed token back into a sentence. So effectively, these encoder and decoder become the input and output layers of the actual large language model, where the LLM itself, all it messes with is those sentence vectors. It does what they call next sentence prediction. We've got a diagram over here to our right. So first sentence in blue, second in green, third in orange, right? Each word here being a token and all goes through the sentence encoder. We end up with one single embedding vector for that first sentence. And then the actual LLM, the next token predictor, right? It works by taking token one as input, outputting token two, taking tokens one and two as input, outputting token three, etc. And what happens now, as I said earlier, the whole quadratic attention, the whole attention RAM issue, what happens now is instead of the model having to keep every single token of every single sentence in its memory to compare against the attention mechanism, what it does instead is it takes every single sentence as one single vector. So now suddenly, if you have a document that's 100 sentences, each 10 words each, previously you had to do 100 times 10 is 1,000 items in your sequence, 1,000 squared quadratic, right? Crazy big. Now, if you have 100 sentences with 10 words on average each, now suddenly your model only does 100 squared for its actual attention mechanism, aka hopefully way less RAM being taken up by that attention mechanism. Now, what does a sentence even mean though? How do we define that? It's a pretty simple, just using different punctuation marks as the delimiters. In this case, they use comma space, or sorry, just comma, I believe, a comma, a period, a question mark, and an exclamation point to separate out sentences. So If this methodology they have here works and does well, then you will probably see in the future attempts to edit what defines a sentence. For example, using a comma, obviously in terms of the English language definition, is not a sentence splitter. It is not, or sorry, it is not a thing that delineates two different sentences. It is actually a thing that goes inside of a sentence. But here, for their purposes, they did comma, probably because some sentences or some pieces of text would be very long if not split up by commas. You might also question, should we be using colons and semicolons, stuff like that. There are definitely ways to mess with this that might lead to increases or decreases in efficiency or whatever it might be. Now, how do we actually turn the embedding vectors of every token inside of a sentence all into one single vector? Well, it's embarrassingly simple, pretty commonly used, I believe, for similarity type metrics and whatnot. But I have been thinking about this for a while now. They did the exact same thing I was thinking, which is they literally just take the embedding vectors of every single token in the sentence, and then they add them up and normalize them with layer norm. So really simple. Every single embedding vector in a sentence just gets summed together and then layer normed. Or I guess you probably should do RMS norm nowadays, but whatever. Now, how does the decoder work though? It's a combination of mass self-attention, aka causal, the regular one we usually use for LLMs, and cross-attention. So self-attention, as you would imagine, the mass self-attention is just a regular causal loop where it looks at every prior token and uses that to create the next token. The cross-attention part, in contrast, it cross-attends to the sentence embedding vector that was given to it by the large center LLM. So our sentence decoder, it takes a kind of beginning of sentence token, takes that beginning of sentence token as input as the first token in its sentence in its mass self-attention part, and then pays attention to it causally, but then also cross-attends to the sentence embedding vector and uses that to iteratively decode to output every actual token, every word in said sentence. And it repeats this process until it chooses to predict an end of sentence token. So the actual final loss function of this model is still just cross entropy loss as you'd expect. But in terms of the actual tensor shapes and everything, it is now broken up into these small little chunks with end of sentence and beginning of sentence tokens instead of just beginning of sequence, end of sequence tokens. Something they used here that is becoming more popular recently, I've noticed, is focal loss, which is this term out front here that changes the traditional cross entropy loss. And if I remember correctly, I believe what it does is it adjusts the probabilities such that entries the model is pretty certain about and is doing well on get weighted less, while entries the model is still pretty uncertain and pretty incorrect about get weighted more. But other than that, you can think of it as just regular CE loss still. Here's a visualization of that. In terms of on the x-axis, we have probability. On the y-axis, we have loss. So higher values mean the model cares more about it. So at any time, the model outputs a high probability, aka over towards the right here. We see that CE loss is the up highest curve here, the actual blue one. It corresponds to this gamma hyperparameter of just 0. Whereas when you increase gamma and you actually use focal loss, what it does is it says, we no longer require a 100% certainty in order to give 0 loss. Now we're going to say if the model has hit 50% certainty or something, and of course if it's correct, obviously, now we're going to say, okay, whatever about the loss, ignore it. Let's focus more so on just leaving loss left over for those tokens for which the model is still very uncertain about, aka further to the left on the x-axis. Now, when it comes to that inner LLM, right, the actual thing doing the next sentence prediction, the important part, it of course can no longer use next token prediction. It instead gets its loss signal from the sentence decoder, right? Does that make sense? However, there's still a piece left over. It's how do we actually know when to end the sequence? How does the next sentence prediction LLM know when to end? Well, a really simple adjustment to make that work here is they just add a separate new linear layer called a termination judgment layer that converts the hidden state of the model at that token into a two-dimensional Boolean vector. So pretty simple matrix. It's just you could do it as either a D by 1 or a D by 2 matrix here output, and just a classifier of is this sentence embedding the final one of the sequence or no, and it learns when the answer is yes, when it should be ending. And then during generation, you have to just let it stop generation once that flag goes up. So the way a regular transformer works, right, is you have to actually do prediction of each token one at a time. And because it is causal, autoregressive, right, you cannot just skip ahead. That's why there's lots of techniques like Medusa, for example, recently that have attempted to speed up generation, is because it is inherently slow, and that in order to get the next output step, you have to take the previous output step, add it to the inputs, and run the whole thing again, right? Whereas with sentence VAE, what we have going on instead is that we have next sentence prediction, right? So it takes some number of sentence vectors, outputs the next one, takes that new one, puts it back into the input, and does the thing again for the one after that, right? But what's interesting here is you can actually, in parallel, while you are autoregressively decoding your sentences, you can, in parallel, take your sentence vectors and use them to decode the actual individual tokens. Meaning that assuming RAM is not your main limitation, which, I mean, to be fair, usually it is, but this also helps with that too. But the actual, in terms of wall clock time iteration limitation, is now way reduced, because while the primary actual main thinking engine LLM is doing the sentence level thinking, you can actually allow that tiny sentence decoder to decode the actual tokens of every single sentence in parallel. So this should massively increase actual speed throughput of the model itself. So to test out this idea, right, what they first did was train these individual sentence level vector autoregressive models, vector autoencoder models, sorry, just to demonstrate that for individual sentences, you could in fact compress multiple tokens in a sentence down into a single vector that represents that sentence by the encoder, and then have those be restored by the decoder. And then once you've done that, really all you have to do is graft that encoder and decoder onto the beginning and end of a, really, you could take a regular open source LLM, just a GPT style system. Except now, of course, the loss function does not come directly onto the GPT itself. It now starts off at the decoder, and the gradient moves through back to the GPT and then eventually the encoder. Key result here to see is that SLLMs still follow this scaling law that you'd expect to have with LLMs, which is hugely important for, does this method actually work? It seems like they have tested it to some degree, and they found that the scaling laws still work. Big, big result there. Now, in terms of the specifics of what they did, in terms of like hyperparameters, we're not going to hit all of them, obviously, but just a couple little assumptions they had in here. They not only used those period, comma, exclamation point separators, but they also assumed each sentence had a maximum of 64 tokens. This is important to prevent going crazy out of distribution. It does introduce, though, a tough problem with this method. That problem being that this kind of idea of splitting by sentences is kind of iffy and weird, as you saw earlier with those delimiters with the actual period, comma, whatever. The fact that we're using comma, huh? Why didn't they use a colon or something? Like, what is the actual unit of this? This is a big problem I was wrestling with in a previous project and did not end up solving. That they just settled for, we're going to go for grammar. The problem also is you now have to do those rules for not just English, but for any other language, right? It adds lots of complication here. It also means that it's tough now for this model to extrapolate to forms of writing that do not match up well to traditional essay article style writing. For example, like bullet point stuff might be weird. Any kind of person who writes in a very rambly stream of consciousness style and doesn't use very many commas or periods or separators, whatever, that'd be tough for the model as well. Or, for example, CSV data, way too many commas in there for that to be a good idea, because now suddenly each individual value in the CSV file is being separated by commas and is therefore its own sentence, which is kind of silly. So there's definitely a bunch of problems with the actual specifics of the regex style delimiter they're using that I think will have to be ironed out in future papers, and that I'm hoping someone can find a very clever solution to that is completely off the wall from just simple sentence separators. They also assume each paragraph has a maximum of 64 sentences. Again, these are for memory reasons. Even if we were to use just the comma whatever separators and periods and things, not only could we have a sentence longer than 64 tokens, but we might also run into the issue of having paragraphs that are more than 64 sentences. And what happens when you have like a 67 sentence paragraph or something? Like this whole thing is just very a bit too constrained in that sense, if that makes sense. So it still remains to be seen how we can hyperparameter tune this thing and make it actually make a bit more sense and hopefully have it learn better, as well as if these limitations are too limiting and ruin things. They are sticking, of course, with the classic perplexity as an evaluation metric. That makes sense for early days of any architecture. It's not preferable. It'd be nice if they would go straight off to benchmarks, obviously, which have their own problems, but it is what you need to see to show scaling laws, which is important here because they only went up to a 1 billion parameter model, I believe. So relatively limited scaling laws. And then rest of the parameters looks to me like they use GPT-2 style sizes roughly. Start off with a small 768 for an actual hidden size. Oh, but no, it's actually some model called Open or OPT, some open source something or other that they used as a baseline. Now, for the actual sentence variational autoencoders, right? The question is, when you do your encoder and your decoder and everything, how many, if you're going to use a transformer layer, how many do you use? They tried out 1, 2, and 4 layers. I wouldn't be surprised if we go bigger in the future, but keep in mind here, it's definitely true. It should be smaller than your primary model. Not that it needs to be technically, but like it makes sense that the task it's doing is simpler than the task that the primary inner model would be doing, right? Here we can see 4 layers obviously does the best, and of course also bigger hidden dimension size does the best. Nothing really surprising there. This little analysis shows 4 different sentences and 4 different number of layers and hidden dimension sizes. How well does this actually do? For these first few sentences, seems like none of the problems have any issue at all. However, something interesting here I'm kind of curious about is the actual use of the commas and whatnot as delimiters. How does that work in their code? They put in right here, this sentence, hello, my dear friend, has a comma in there. And certainly that was a separator now suddenly, where these are 2 different sentences, according to the model. But does the model not have an easy way to then output and show that there's a comma there? It seems to me like they should have probably used comma, period, exclamation point, etc. as their end of sequence tokens instead of doing its own separate end of sequence token. Because you can still have multiple EOS tokens and just have them each behave the exact same way, but the distinguishing feature between them is the actual token that gets displayed in the text. Whereas here, for some reason, they have like a triangle, I guess, to show the separation, and then they put a comma at the end, which I believe means the model is messing up somehow, but it's very unclear as to what's happening here. Then look at a sentence like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? There's a question of how much positional information is that autoencoder, that middle sentence embedding actually displaying. The smallest model with a 768 dimension size really had trouble with the ordering of these numbers and even like what the numbers were, because the word knights ended up in here, right? When we get to the largest size they tested out, it was actually able, except for one switch up, to do the words, sort of kinda, but we seem to have it wanted to do an end of sentence something or something in here. It definitely could use a larger model. And I really think a big thing with this will be that they didn't delve into this paper. I need to stop using the word delve. It's so annoying. Uh, a thing that they should approach is how exactly do we think about and reframe our idea of positional encodings given this new little setup is the question. Then when you get to weirder words and phrases and things, for example, this is a ha 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 period, and you, how do you handle that odd number of periods, right? It seems that there was no triangle split happening here, and the actual ha 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 word was tough as well. How does the model inside that embedding vector convey that it wants to do the aha a certain number of times, right? Or here is, I believe, a different language of some sort, Asian something, not quite sure. And as you can tell, smaller model does not do well at all. The larger one does get it just fine, though. That's more of a linguality thing, and they didn't actually test what I want to see tested for other languages, which would be how do other languages use um, sentence separators, commas, periods, whatever, or their own things. How do they use those symbols, and how does that affect things? I want to see an analysis of that. We do see here some scaling law graphs that look about as they should. When going past the actual vector autoencoder piece and looking at the full end-to-end SLM with the autoencoder decoder on the ends and an LLM in the middle, it found it to be about 2 to 3 times faster on average than regular LLMs. This is thanks to that efficiency sake of having to do uh, less RAM taken up also, but just fewer actual pieces of the forward pass and being able to do parts of the forward pass in parallel. Interestingly, the larger number of the model parameters, the smaller the proportion of inference cost occupied by sentence VAE, and the more obvious the speed benefit. So that sentence VAE piece was pretty small. Hidden Dimension of 2048 did pretty well right there. I imagine you bump it up a little bit higher, and it can really be consistently just doing any sentence, maybe even larger still for bigger languages. But at a certain point, this sentence VAE part doesn't need to get that much bigger. Its job is relatively simple because it has such a rich input vector of that sentence vector, right? Meaning, as the model gets larger, the job of the actual autoencoder shrinks in proportion to the actual main piece, which is the LLM, the inner GPT in there, that actually has to do all the logic and reasoning and prediction of the next sentence. They also observe that the perplexity of these SLMs that they made with their whole VAEs on the beginning and ends was better than that of the baseline OPT models. To be fair, I believe the OPT model is relatively old, could be wrong though, and it's never clear with these things. Did the authors actually do a very good job at replicating the baseline in terms of using the same training data and whatnot? That's always an issue, and I don't know for certain what they did here, as well as the fact that for a model like this one today, creating a accurate comparison baseline is pretty tough. It's not always fair to compare off parameters. Sometimes we compare based off isoflop, sometimes based off RAM usage, right? There's different compute constraints you might want to hold constant while comparing against. And I think I might have missed it here, but I'm not even sure which one they actually did. I believe they did parameter count, I think. But it's not always clear which compute constraint you want to hold constant while comparing. So I would really love to see a more thorough analysis of that. I might have missed it in an appendix somewhere or something, but it's not that I know of. But it could be the case that, in fact, this SLM paradigm actually does enable better thinking because the model can now process natural language at a higher sentence level. It might be that that level of analysis is actually superior to the token level. Of course, limitation on token, on like number of tokens in the actual like token level is first and foremost words. Unless you want to start creating multi-word tokens, you really are limited in terms of your actual token size and how big they can get. And second of all, creating larger and larger vocabularies greatly increases parameter count and leaves you with so many subword tokens that just never get trained on, such that your RAM taken up, period, and during training is now much worse, taking up like thousands and thousands of vectors that are just subword tokens that never even get used is not a good idea. Hence why you can only get so large in vocabulary size. Vocab sizes have been increasing lately by a good bit, but it might be the case that actually having the model think at the sentence level, the kind of more conceptual level, might make sense. And this has actually been shown from some recent work. I know Meta's recent paper, multi-token prediction, I think it was called. They found that the ideal, instead of doing next token prediction, like one token head prediction, they found it was more ideal for a model to predict simultaneously 4 tokens ahead. And the model is pretty good at doing that. I also seen neuroscience, not neuroscience, but computational neuroscience research trying to hook up LLMs to brain scan decoding to predict what the human's actually hearing. And they also found that the human brain seems to think in an increment that was on average about 4 tokens long, meaning what's that, like 3 point something words, 3 words or so, 3.1 maybe. Next thing being longer context length. Because our actual primary model is dealing with sentence level tokens, there's so many fewer tokens, and the huge memory limitation with transformers obviously is the attention mechanism. Now suddenly this allows for really impressive far longer context length. And then they didn't mention this part. I'm hoping, I believe, that the attention mechanism should also have an easier time paying attention what it's attending to. Reason being, now that we have so many fewer tokens, so many fewer actual residual state embedding vectors going in, and that attention tends to fall apart a bit when it has to attend to too many tokens at once, given that it does use a softmax, of course. It should be the case here that, or I hope anyways, I predict to be the case, that the model would have an easier time picking up on information from very far back in the sequence and then using it, which may help solve the actual long context problem, which is, can the model even correctly figure out what to attend to? Could be wrong there, but that's a prediction. All right, that is it for today in this paper. I hope you enjoyed it. Keep in mind, my hope is within a month or two, hopefully sooner, honestly, if I could, I want to do an actual full code tutorial, step by step, matmul by matmul tutorial on this, and have a mini, micro, very small version of this working on a tiny stories dataset relatively soon. I have some stuff to do before I can do that. I have some like to-do list items to check off, but I would love to get to that. That would be so enjoyable, and I want to do more coding tutorials like that in the future, but we shall see. Don't leave yet. If you got this far, you're going to love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.